Okay, so finally, this is our last new concept for simple harmonic motion, and this is still to do with energy, and this we will call resonance and forcing of simple harmonic motion. So we talked last time about damping and how energy is lost in simple harmonic motion in real situations where there's friction. So what we're going to be talking about now is resonance, and the way that resonance is really adding, forcing is really adding energy to a simple harmonic oscillator. So we can add energy to an oscillating system by applying, oops, that doesn't look like applying. So by applying a force to it, we can achieve resonance by applying the force at the same frequency as the oscillation. What that means is, for example, the most obvious example is if we have a little brother or sister who's sitting on a swing and they're swinging back and forth. If we push them once every swing, we can give them a much bigger amplitude on that swing. We can also kind of do the forcing ourselves by shifting our weight as we swing, but it's easier to kind of visualize if we think about someone pushing the kid on the swing. So we can do that as an example. So e.g., when we push a kid on a swing, we can add energy to the system. If we push, oops, if we push them once every swing, their amplitude will gradually increase to a maximum. Okay, so how often should we push in order to maximize this amplitude? This is the question that we're asking when we're thinking about resonance. So this increasing it to a maximum is what we call resonance for the motion. So what we can do here is we can just define that here. So increasing to a maximum, this is called resonance. Okay, so what we'll do is, I'll just define that a little bit more clearly. So that's called resonance. So to achieve resonance, we must force the system at its natural frequency. So in other words, if we push at the same frequency that the thing swings by itself, so natural frequency is that's the frequency that we, or the period that we worked out when we were working with with the, for example, the pendulum and the mass spring system. So let's have a look at an example here. So we'll have a look at this one here. So here I have a mass on a spring, and I can turn this little driving system on here, and this will push this spring with a frequency that I can decide. And we can see that it then gains some energy and starts oscillating, but I'm probably not driving this at exactly the right frequency to get a really big amplitude. And so I need to figure out what the natural frequency is of this system first. So I've set this up to have a mass of 2 kilograms and a spring constant of 100 newtons per meter. And so if we have a look at that here, so we'll look at a practical example. So example. Whoops, sorry. So a mass of 2 kgs is oscillating on a spring with constant K equals 100 newtons per meter. At what frequency should we force it to maximize, to achieve resonance, we can say. Let me get rid of this little thing. Okay, so the short answer is at the natural frequency. And that is, well, we know that T is equal to 2 pi square root m over k. So in this case, that's 2 pi times square root 2 over 100. So we need to figure out what that is. 2 times pi times 2 divided by 100. And then we want to square root that, and we get 0.89 equals 0.89 seconds. So the frequency, the natural frequency, is equal to 1 over t, which is 1 over 0.89. Remember, the frequency is always just the inverse of the period. So that's equal to 1 divided by 0.89, which is 1.12. 1.12 hertz. So if we drive it at 1.12 hertz, we see that we should be able to get it to resonate. So let's have a look and see if the amplitude gets significantly larger if we change it to that. So I'll make it 1.12. Let's see what happens to the amplitude here. We can see that the amplitude significantly increases to some maximum. So the amplitude now is quite a lot larger than it was. We're up at like at 7 meters or 7 centimeters. I'm not quite sure if this is meters or centimeters. What I'm going to do is just move away from the resonant frequency now. So I'll just grab my mouse. So if I decrease this, you can see that now if I'm oscillating it at a frequency that's too slow, I'm sometimes going to be pushing against it and sometimes with it, which means that I'm going to be kind of cancelling out its motion. But if I approach the resonant frequency, you can see the amplitude starts to get a little bit bigger. Now I'm getting reasonably close. It gets bigger, but then it kind of dies away again. It never quite reaches that maximum of 7. And when I get to the resonant frequency, you can see that now the amplitude is getting much bigger. Okay, and it depends on the spring constant and the mass, obviously, what frequency I'm going to be forcing this thing at. So now we have a huge amplitude. And I can show you, if I add a bunch of resonators here, these all have different spring constants. And you can see that only this one is oscillating at the right, we're going at the right frequency. So these higher spring constants should have a higher natural frequency. So if I just start scrolling through these, I can find a frequency where a different one is going to resonate. So now I'm at a frequency that's closer to the second one. If I keep increasing the frequency here, eventually that one will die out. And I'll now be at the natural frequency of the third one. Continue to increase. I'll be at the natural frequency of the fourth one. And note that all the other ones are not really oscillating very much at all, because this frequency is not the resonant frequency for the other ones. Okay, so I'll just pause that and just summarize what I've said. So, if we force it at this frequency, amplitude becomes huge. Okay, and this is called resonance. Okay, so one last little thing about this is if we force it at a frequency that's not the resonant frequency, then we won't get a very big amplitude, and it's highly sensitive to frequency. So we can draw a amplitude versus frequency graph versus forcing frequency. And we need to be able to recognize this as well. So what this graph will look like, let's go back to my original color, is we'll have a vertical axis that has the amplitude of the motion, and we'll have a horizontal one that we will call the driving frequency or the forcing frequency. And that's in hertz. And what happens is we have some frequency that is the natural frequency, which we'll call F0. That's the natural frequency. And for a mass spring system, the natural frequency depends on the mass and the spring constant. For a pendulum, it will depend on the length and the acceleration due to gravity. And so what we see is we have very low amplitudes, and then it just spikes. It gets really big at the natural frequency, and then it dies away again. If we had more damping, what the system would look like is this graph would look the same, except, so if there's more friction in the system, then the amplitude will just be slightly less at all points. So this one here, there's more friction, so more damping. But we have a peak at a very precise frequency. So amplitude is maximum when forcing frequency equals natural frequency. So just to summarize here and to remind you of what the key terms are here. So resonance occurs when we force a system at exactly its natural frequency. And the natural frequency is determined using our equations. T is equal to 2 pi square root m over k for spring system, and T is equal to 2 pi square root L over G for a pendulum. So the kid on a swing, for example, we would work out their natural frequency based on the length of the swing, and then if we force it with the same period, then we will achieve resonance. So note also that F is equal to 1 over T.